Let's talk about the Traveling Salesperson Problem, or TSP. The basic problem is, given a map with some cities on it, visit every city exactly once and come back to your starting city at the lowest possible cost. Cost could be distance, it could be time taken to drive from a city to a city or fly, it could be fuel spent, it could be some combination of those things. So here's, I think, 49 large cities in the US. This tour was done 50 years ago or so. So this is what a solution typically looks like. This was first named the Traveling Salesman Problem in 1949 by Julia Robinson, who's a famous mathematician. You could go read about her. It had been worked on before that, but it wasn't called the Traveling Salesman or Salesperson Problem. It was called the Hamiltonian Path Problem. People these days mostly call it the Traveling Salesperson Problem, realizing that men aren't the only kind of people who travel and sell things. But you'll also still see people calling it Traveling Salesman Problem. It's important not just for geographical actually driving around stuff, but it's actually a major tool in genome sequencing. And that's how a lot of genome sequencing gets done these days. It's called shotgun sequencing, where they take a DNA sequence, the little molecules, and break it up into a bunch of small bits, sequence each one, and then try to look for overlaps between them. And the amount of overlap is related to how much distance there is between the cities. If there's not much overlap, then that's more distance between these DNA fragments. So let's talk about some conceptions and misconceptions about the Traveling Salesperson Problem. Let's read some of these. If you just say, wherever I am, I'm going to go to the nearest city that I haven't visited yet, and keep doing that for all the cities on your map, does that give you a guaranteed optimal answer? Well, here's a question. Can you design a set of cities in 2D where, starting at one city, following that method, you end up kind of trapped and having to take a long drive back to the city you started at, or even just somewhere in between? It turns out it is possible to do that. So this statement, that it's not guaranteed optimal, but it's usually pretty good, that's basically true. Are there n factorial possible routings when you have n cities? That's true, right? Just put the cities in the order you're going to visit them. There's a little quibbling about, well, you get to choose which city you're starting at, but it's basically n factorial. N factorial is really large, right? It grows really quickly, faster than exponential. Anything whose time takes an exponential amount of time is basically computationally not possible. So what do you think about this statement? Well, it turns out that we don't just list all possible routes and evaluate all of them. There are algorithms that can shortcut and like throw out bunches of routes and stuff. So it's basically true that computationally the TSP is not a hard problem. There are algorithms that do a good job for us most of the time. How about it takes to find a guaranteed true optimal solution, that time grows exponentially in the worst case. That's true as far as we know. People have been working on problems like this for 50 or more years and haven't come up with a way to solve them in a way that where the time grows polynomially. So in the worst case, as far as we know, this is true. You might be starting to get suspicious now and wondering, when is the other shoe going to drop on this category? We'll see. All right. Is it true that there are reasonably elegant algorithms that give pretty good, but not guaranteed good, optimal solutions reasonably quickly, in that they don't take an exponential amount of time with the number of cities in the problem? That's basically true. And you can go look up some of those. The Christofides heuristic or algorithm is one of them, or the Lynn-Kernighan is another one. Somewhat fancier algorithms that most people would not call elegant, but they get the job done. Can they get within 3% of optimal reasonably quickly? Yep, someone did a computational study, and that was basically true. How about what's the largest known guaranteed optimal solution? Do you think it's like 80,000 nodes, 8,000 nodes, 800 nodes, 80 nodes, nodes meaning cities, or is it 800,000 nodes? It turns out it's right around 80,000. There are other problems people have worked on that have millions of nodes, and they haven't found the guaranteed optimal solution to those yet, but they're got within like 3% of guaranteed optimality, so that's good enough for most purposes. How about this one? The current and long-standing champion software for TSP is called Concord. It's quite complex, and it uses integer programming methods rather than just saying I'm going to go to the nearest city that I haven't visited yet or something like that. That's true. It's a big code base. You can download it for free. You can even use it online for free, and it uses really advanced integer programming methods. How about this one? Reasonable sized TSPs, and by reasonable I mean like dozens to maybe 100 nodes. Are those too hard for us to solve in math560 using Excel and Solver? Well, this one's up for debate. There's probably a way to do it in Solver using the evolutionary algorithm and the constraint called all different, but I haven't actually had time to try it, so that could be someone's project. So we'll put a question mark here. And then how about this one? I talked about DNA sequencing happening by matching things, matching little subsequences together. Does that need guaranteed optimal solutions, or is it okay to have just within some small percent of optimal? I don't know the answer to that one either. So that's something we could go research if we wanted to. All right, so you'll see statements like this are on the web that say, vehicle routing problems, traveling salesman being one of them, salesperson, are inherently intractable. So what do you think? Is that true? And this is on a website by Google developers that offers some operations research software. So can we wrap all this up and say, is this true? Vehicle routing problems, including traveling salesperson, are inherently intractable. Well, I guess in theory it's true. As n grows beyond about 880,000, beyond 80,000, maybe it takes too long to find a guaranteed optimal solution. But if you're happy within a few percent of optimal, then I say they're totally tractable. And we'll talk about vehicle routing problems other than the traveling salesperson problem in the next video.